All right, so we are going to pick up exactly where we left off with the previous video. So we are continuing our implementation of the Linky linked list quote-unquote library. So we are going to now work on functions that allow us to add element to the list. And we're going to start with actually the most straightforward one, which is going to be adding a new element to an existing list at the front of that list. So this function, we're going to write its prototype first. It's going to return nothing. It's going to be called node add front. And we are going to continue following the convention that the first argument is always a pointer on the head of our linked list. And then I need a pointer on a new element. So I'm going to call this element. There we go. That's going to be what we are trying to add to the list. So we have our prototype. So this one is not going to have to be iterative recursive. We're adding at the front of the list. So it's not an operation that's going to require us to go over every element of the list. When we are trying to add at the end of the list, yes, then we'll have to go through every element of the list. So there are going to be two ways to go about that. One way is to go through the list recursively. The other way is to go through the list iteratively. But we are not there yet. Right now, we just add to the front. So we don't have to worry about iterative versus recursive, which means that we can implement our function right here inside the file linky.c. Remember, this is where we're going to put all of the functions that do not have an iterative or a recursive version. All right, so how are we going to proceed to add something to the front? Well, let's take a look at our whiteboard there. It's always better to visualize first and implement after, okay? So let's say that we have from the main a pointer p, okay? It's going to point to a list, and I'm going to do the general case, okay? A linked list that has more than one element. So there we go. This is pointing to the first element. Let's put the value 1 inside of it. Second element will have value 2 to make it easy to distinguish them. So there's a null here, okay? There's no third element. So this is the situation that I have. This is a linked list that I have. So this is the main. And when I call my function is going to have an argument list. And that argument is a pointer on pointer, right? So if pointer p is at memory address alpha, okay, I'm going to pass the address of p. So that means that list is going to point to this pointer p. Okay. And then the other argument is going to be the parameter, is going to be stored in the parameter element, which is a pointer, and this one is a pointer to a node. So that means that somewhere I created a third node. Okay, let's call it, let's put data3 in it. It has null as next pointer, and I have a pointer to that node. Okay, for example, I use the function node underscore create that we wrote in the previous video. So this is what my my function receives. What do we want to do here? What we want to do is we want to add the new element to the front of the list. So maybe I should have put the number 0 here, because 3, 1, 2 is going to sound a little unnatural, weird. So let's say that I have 0, and I want to insert it at the beginning of the list so that I have 0, 1, 2 in my list. What do we need to do? So we need to make sure that the pointers are not null, okay? So we have some safety type verification, okay? Now, if you gave me a pointer here, p, that contained null, then that would be easy, right? Let's draw the scenario here below. If p contained actually null inside the main, then I would have list, point to p. I would have this new element here referred to by element, okay? So the top is one scenario, the bottom a third of the whiteboard is another scenario, okay? So this is supposed to be the main, this is supposed to be the main, and this is supposed to be my new function called add front, node add front, okay? So if you give me the address of a pointer that contains null, then for me to add in front of this linked list, this new element, is simple. That I remove this null. So that's what I'm going to do right now. There we go. Erase this null. Replace it by the address of the new element. And after I do this, you can use P as the pointer to the head of a linked list that contains only one element, the new element that I wanted to add. This is when P is null. Easy case. When P is not null, we have a little bit more work to do, okay? And I'm going to use a different color to show you how we are going to change the various parts of that point to another part. We want first to say that this element, because it's going to end up at the front of the existing linked list, it needs to tell me that the next element after it is, well, the front of the existing linked list. So we are going to have to add this green arrow. And then we are going to have to say that the new head of the linked list is the new element. And now when you look at the green arrow, you see that P points to this element here, which points to what used to be the first element of the linked list, which points to the second element. We kind of change the chaining of the elements, the linking of the elements here, so that we have a new flow that gives us the new linked list. That's what we want to do in code. If you jump into the code and you don't have a clear ID like this in terms of diagrams, in a clear picture in your mind of what you want to do, you're going to probably mess up. So I really advise you, before you jump into the code, to know exactly what you want to do in terms of changing the linkage, between the various elements and the various pointers. Once you have established that, and you can even go to the level of saying, well, first I want to do that, and then I want to do this, number your steps. Once you have this clear ID in your mind, then it's going to make implementation a lot easier. Otherwise, it's very easy to mess up this kind of stuff. So let's go back to the code. We are going to start with the ID, the simple one. Actually, we're going to start with safety. Safety means if list equal null, return. You don't give me the address of a pointer to an element of type node. Okay, I cannot do anything. If you tell me that you are trying to add to the front something that is null, return. If element is null, you are not trying to add anything actually to the front, well then fine. I'm not going to add anything to the front, but I can do that very efficiently by just not doing anything, okay? So this is like the safety checks. After that, so now we know that we can dereference list because we checked that list was not null. So if star list, so that's going to give us a pointer on the current head of the linked list. If it's null, well, that's the case that we had at the bottom of our whiteboard here, okay? That we have a pointer on a pointer. That pointer originally contained null, so we are going to link it to the new element, and that's it. That's all we have to do. So how do we achieve this? Well, we're going to write star list equals element. And we know element is not null also. We already checked for that, okay? Else, and this is a case where we have a little bit more to do. So if it's not null, then we are in the top case here in our whiteboard, okay? We're like right here, right above. So we have two modifications to do. First, we need to say that the next pointer of the new element here is going to point to the current head of the linked list. So how do we write that in code? So we are going to say element arrow next equals star list. Okay? So there are two difficulties. One difficulty is to come up with the ID that we need to put this green arrow here. Okay? And then the second green arrow here. The second level of difficulty is once you know that you want to do this, how do you translate it into code? Okay? So be mindful that when you don't know what to do, it's either because of the design aspect or it's because of the syntax aspect. Syntax aspect is generally easy to fix. It just takes work. Okay, practice, work, and remembering, memorizing, those different syntaxes that we cover in the lecture, in the reading assignment. Next, what do we need to do? Well, once we have taken care of that first green arrow, the second green arrow is about saying that the head of the linked list now is going to be that new element. And at no point we had to go and iterate over the linked list or recurse over the linked list. We just manipulated, the pointer to the head of the linked list and the new element node. And that's it. That's all we need to do to add something in the front of the linked list. Let's save that for now. Let's compile. So it doesn't matter if we compile the recursive or iterative version, okay, because our new function here is neither recursive or iterative, so it's in linky.c. Node at front, expected expression before equal token. So we have a problem here. Let me see, void node at front. If list equal null, return. What is it complaining about? Statement before token. It's because I closed my parentheses too early, didn't I? Yes, that's it. All right, let's try again. All right, it's compiling. A.out, it displays the list. But I haven't tested at front yet. So let's try that. So linky.h was not even saved. Wow. All right, now it's saved. Linky test.c, we are going to say that. So let's call this node1, n1. Okay, node1. I create the node, so I can, instead of initializing to null and then immediately creating the node, I can do this. Okay, so I have a node1, I display the list. Then I'm going to say I have a node2, node create, and I'm going to put the value 23 inside of it. And then I'm going to say node add front. I'm going to pass the address of n1. And I'm going to say I want to add n2 in front of it. Okay. Instead of using n1 and n2, I'm going to try to have like some sort of standard here. N is going to be a pointer to one single node, okay, and then node star my list is going to be originally null. As soon as I have one node, I'm going to say my list equals n1. Okay. What else? And so here I'm going to be able to say my list and n2. Okay. And then after that, node display. And I'm going to display my list. All right. Let's see how many syntax errors I was able to show in that little piece of code. Okay, not that many. Good. 0 is a good number. And then let's run a.out. So not display n1, it displays 42. So I should do a line break here, because otherwise it's going to be a little confusing. So hold on. Let's add that printf here after the not display. Okay. So I'm going to display the first state of my linked list, which contains only one element. There you go, 42. Then I call add front. And I can verify here that once I display the whole list again, then I start with a new element. And then after the new element, I successfully chained what used to be the first element of the linked list, which is now the second element. Okay. All right. So we are starting to get to the point where we're going to be able to make some interesting tests. Let's go back to linky.h, because now that I did add front, we're going to keep working on adding, and then we'll work on deleting elements, okay? So the next one that I want to play with is I want to actually do the add tail, okay? So the opposite of add front, it's going to add at the end of the list. So void, wrong window, void node add tail. And again, I follow the same, always the same convention. Okay. I want to add to the tail of this list this new element. All right. So I'm going to take this, take the prototype of that function. And now I am back to a situation where I could implement this iteratively. I could implement this recursively. So I'm going to start with the iterative version. So here's my prototype. All right. And now we're going to talk about how to go about implementing this iteratively. So it's going to be a little similar to not display, okay? It's the same way that the recursive version is going to be also a little similar to not display, because we want to iterate over the list. So there is going to be some similarity. The first similarity is that if you give me a list that is null, I cannot do anything for you. If you give me an element that is null, well, technically you ask me to do nothing. I can do that very efficiently for you. Here we go, I did nothing. Then I'm going to use a pointer p initialized to the star list, which is actually the value of the pointer on the current linked list. Okay, so I'm going to initialize this temporary pointer, and then I'm going to do if star list equal null. So if you ask me to add to the tail of a linked list that is empty, okay, how do I do this? Well, the linked list is empty, so adding to the tail is going to be the same thing that adding to the front. So I can just do star list equal element. And that's exactly what we did actually in the add front method as well, okay? Now, the interesting case is when you ask me to add an element to the tail of a linked list, and that linked list is not empty. So what are we going to need here? We are going to need a loop that's going to keep advancing the p pointer to the first element of the linked list, then the next one, then the next one, then the next one, and it's going to stop when it is pointing to the last element of the linked list, and then we are going to add one element after that. So how do we write this? While p arrow next. Okay, so p points to one element of the linked list. Then what we say is, as long as you have a next pointer in that element that is not null, so I could write while p row next different than null, okay, but while p row next is going to work just fine. So as long as this is not null, what I want to do is I want to say that the new p is going to be p row next. So I want to advance in the linked list, and I don't need even the curly brace here because I have only one statement to do. So this is going to cause me to reassign constantly the pointer p so that it points to the first element. The first element has a next pointer that's not null. Okay, take that value, put it in p. Now p points to the second element, and so on and so forth. Okay? And then, when I'm done with that, when this condition becomes false, that means that I'm pointing right now to a node, and that node has a next field that is equal to null. Perfect. That's the next field I want to modify. I want to say that this node's next field is going to be containing now the address of the new element. And therefore, I put the new element at the end of my linked list. Okay? All right. So a lot of similitude with what we did, okay, before, but it's kind of a merge between not display for the iteration and add front here for this part of the code right here. What I'm going to do now, I'm going to get rid of compilation error, if any, and then we are going to test that together. So I'm going to go back to my main, and I'm going to say, now that I added successfully to the front of the list, I'm going to add to the end of the list. So node star and free equal node create, and I'm going to put 99. So the list is going to go 23, 42, 99. Perfect. Okay. And then node add tail, address of my list, and free. Node display to make sure that it was added properly. And then printf of the new line, just to make it easy to read. Okay? All right, let's compile again, and let's run it. So initially, I have only one node, 42. Then I add to the front the value 23, 23, 42. That sounds reasonable, okay? Then I add to the tail the value 99, 23, 42, 99. And I've been compiling the iterative version, so I'm using this version of the node add tail function, which is good because I don't have yet a version of the node add tail version that's recursive. Like if I was trying to compile the recursive version, here we go, it would tell me, hey, I don't have an implementation for that function. So this is what we're going to work on now. Now we're going to implement the node add tail function, but we are going to implement it recursive style. So let's go into the linky-recursive.c file, and we are going to go ahead and say void node add tail. And again, same is going to have the same prototype, okay? So node star list node star element. And now I can start thinking about the implementation. So again, there are going to be some commonality, okay? For example, those little safety checks at the beginning, definitely I want to do them also in the recursive version, okay? You should give me a null pointer, so you don't give me a pointer to a pointer, forget it. If you give me an element that's null, do you want to add it at the end of the list? Sure, consider it done. No problem there, okay? And then we are going to have like somewhat a similar logic, okay? Our first test is if star list equal null. So if you're trying to ask me to add something at the end of a list that is empty, no problem. Star list equal element. So this has been working, for add front. This has been working for node add tail iterative version. For the recursive version, that's always the same thing. If the list is null, there's no list yet, then adding to the front, adding to the tail is the same business. Else, if, and now we're going to test some more interesting stuff, okay? Now we're going to say I can dereference star list because I made sure list was not null, and I'm going to look at the next field of that first node that is in the beginning of the linked list. And I'm going to check if this is equal to null. So if this is equal to null, that means that this is it. I am looking right now at the last node of the linked list, okay? Star list point to the last node of the linked list, so I can add my new element right after this node. So star list, that gives me the pointer to the node. Next, a row next, that gives me, actually, I'm doubling the arrows here, sorry about that. A row next, that gives me actually the access to the next field, and I'm going to say that this points now to element which I know is not null. Okay. So one part that's missing, the recursion. What if the pointer you gave me is not null, the element is not null, the head of the list exists. Sorry, the head of the list is not null. The head of the list is not the last element of the list, so it's not a list of one element. How do I recurse? Well, I'm going to call myself recursively node add tail, and I'm going to ask myself, so first, what is my element? That's the easy question, right? My element that I'm trying to add is still the same. But now, where is that pointer to the next element in the list? So we're going to start with star list, okay? Because list is a pointer on a node, so I want to have access to the pointer on the node. And then I want to check inside that node what is the value of the next field. That's my pointer. That is the pointer that I want to pass to my recursive call, okay? But I don't want to pass the pointer itself, the value inside the pointer itself. I want to take that pointer, and as with our previous recursive implementation of node display, I want to take the address of that pointer and pass that to node add tail, okay? And this is the important part. This is a difficult part. This is a recursive call part, and the most difficult part is indeed this. So don't hesitate to ask questions. on Piazza, on Forum, whatever we use this semester, or come to office hour. Okay, if this doesn't make sense after this video, don't freak out. Just come to office hour, ask us a question. We'll work you step by step through that and help you understand it. Okay. All right. And that's pretty much all we need to do. That's it for adding to the tail of our linked list. So we have a version that's recursive, a version that's iterative. We tested already the iterative version. Let's try to test the recursive version. So I'm going to compile the recursive version. I'm going to run it. Same result. It works exactly the same way. Okay? All right, so where do we stand here? We have, let's see, we have the add front, we have the add tail. So we took care of everything that add element to the front and the tail of the list. We did the iterative recursive version of add tail. So we are good for both versions of add tail. Add front had only one version. Now the next thing we are going to do is we are going to jump into the functions that actually delete an element from the list. And for this version of the linked list, we are going to delete either at the front of the list or at the end of the list. So the first function we are going to tackle is going to be void node del for delete front. And I'm going to follow the same convention again. Okay, I want to delete the first element that is at the front of this list, and I give you the information about where the list is by giving you the address of a pointer to the first element of that list. So just like add front, didn't need to be iterative or recursive because you just work right here on the front of the list. Del front is going to be exactly the same way. So here we are. I'm going to go into linky.c, and I'm going to paste my prototype, and I'm going to write the code for this function right here. So how are we going to manage this? So we want to remove, so we are going to remove a node from the head of our current linked list, okay? As we remove it, we are going to unlink it. We are going to also free it, okay? So what does it entail to remove an element? Let's go back to the whiteboard real quick. So I'm going to clean this up. Hold on. Select as much as I can here. Try to delete it. There we are. There we are. Okay, so what does this entail? Let's start with a simple scenario. We're going to try to mimic what we had before, right? So inside the main, I have P1. Okay, P1 points to a linked list. And I'm going to say, without lack of generality, I'm going to say this linked list has two elements, but as long as it has at least one element, we're good, right? So here's my pointer P1 to a linked list. What does it mean to remove actually the first element? Well, that means that I call a function, my function that I'm trying to write right now. It is going to have a pointer list. The pointer list point on P1. And what I want, the change that I want to affect is I want to change this and have P1 point directly to the second element of my linked list. That's the first thing I want to do. And then, number two, I want to deallocate this node right here. Okay? So it sounds relatively straightforward. Let's see how we can implement this. Okay? So first I need a node pointer P. Well, first I need my safety, right? So I'm going to say if list is equal to null, then return. Okay? Again, same safety check that I've done all along. Then the next thing is for me to declare a pointer. I'm going to call it P. Okay? And I'm going to initialize it for now to null. I'm going to use that pointer to save actually the head of the list that I'm going to remove. Okay, so I'm going to save that, and then I'm going to modify it, etc. I need two pointers. All right, so node star p equal null for now. Then if star list. So if I have a list that is already null, I have nothing to do. Okay, so I should actually add it here and do if star list equal null, return. I don't have anything to do. Okay. Removing the first element of an empty list, sure, I can do that very efficiently by doing nothing. So this allows me to not have to make the test here and instead just assume that star list is not null and go ahead and say, for example, I want to save the value of the next element, the second element of my list. And this could be null, okay? But even if it's null, I want to know that value and save it in my pointer p. So p is going to be equal to, and since I'm assigning it right after initializing it, I'm going to do it here. Star list, a row, next. Okay? Problem with the shift key here. Star list, a row, next. So going back to the diagram, that means this pointer here, right here. Okay? Whatever was here, I'm putting inside of my pointer p. So I'm saving the address of this element, pretty much. So going back to the code, what do I do once I'm done saving the address? I'm going to free the current first element of the list. How do I find it? Star list. Okay, it didn't move. And then, once I have freed this node, then star list equals p to assign the element as being, the new element is now the head of the linked list. Does that make sense? So let's try this. Node del front, we are going to go here to linky test.c, and we're going to try it out. So I have a linked list already here. I'm going to just call node del front, and I'm going to say I want to delete from my list. Okay, and then I just have to display pretty much a resulting list with a backslash n at the end. There we go. All right. Let's give it a shot. So compile this. Doesn't matter if we compile recursive iterative because we have only one version of that function. We have added, so we started with 42, added 23 at the front, added 99 at the end, then remove 99 from the end. Okay? And so that's this node del front. Did I say del front or? Yes, I did del front. I didn't want to do del front, did I? Yes, I did. Sorry about that. Okay, I'm confusing myself. I hope I'm not confusing you. So I deleted the front. I was thinking I was deleting the tail, but I'm deleting the front, so I'm deleting 23, and that's it. 23 is gone. I'm left with 42 and 99. Okay, that's it for del front. So now what we can do is we can look at the other two function that we have left to implement, and you can guess them, okay? That's going to be the two version of node del tail, not trail, okay? And again, it's going to take a node pointer and pointer name list as parameter. So let me take this, and this one I'm going to have two versions. So I'm going to start with the iterative version, okay? So del tail iterative version is going to be a little bit more involved. So let's put it here. All right. And actually, I'm going to prepare also the work for the recursive version. There we go. There we are. And the recursive version is going to be implemented here. So not del tail, iterative, and recursive. And this is going to be, this function is going to be a little bit more involved. So let's start again, like we always do, by taking a look on the whiteboard at what it's going to look like. And I'm going to start by cleaning all of this first. There we go. So let me grab a pen here. There we go. All right, so let's say that we have a linked list, like, we're going to consider a different case, okay? So if we have an empty linked list, deleting the tail of an empty linked list again, we can do that without effort. But we can have otherwise a linked list with just one element. Okay, so this would be a null here, and there is one element right there. Or we could have a linked list with more than one element. So in this example, I'm going to use 2 elements. Okay, so 23, 42, maybe. All right, so it's going to matter here because what we want to do is we want to, and I'm going to change color to show you what we're trying to do, okay? We want to remove the last element of the list. So when it comes to a list that has one element, I want to remove that one element, which means I want to put a null inside the pointer that you gave me, the pointer of which address you gave me, okay? So of course, when I do this, that big X, red X on a node, that means that I'm going to also free it to not have any memory leak, okay? But that's pretty much what I want to do. When it comes to a list with 2 elements, I want to check first that I have my pointer pointing to an element that has actually some sort of address here. If it has null, then I'm in the first scenario, the one on top here. If it doesn't have null, then I'm going to consider that potentially I have one or more element after that. Well, I'm going to check. I'm going to check the next value for the element here. And if I realize that it's null, then I'm going to modify this pointer here. I'm going to replace this value by null, and I'm going to deallocate this element. Okay? All right. So it's kind of like, it's a situation where I want to look ahead. You know, by one element, I want to always make sure that, okay, I'm pointing on one element here, but it's either I need to remove that element, so I modify this pointer that I have right now, or I need to modify the element after it. So to do this, we're going to have a structure in our code that's going to be a little bit more involved, okay? We are going to have, so our basic verifications, okay? If list equal null, forget it. If list equal null, return, as usual. I don't have an element here, so I don't have to check if the element is null. But now that I know that for sure my list is not null, I'm going to say, okay, let me take a look and see if star list row next is not null. So when I write if star list row next, is the same thing as if I wrote if star list row next different than null. Okay, just again repeating that so that it doesn't confuse anybody. But what I'm doing here is I'm checking the next pointer of the current node that I'm looking at in my list. Okay, so my pointer list points on a pointer that is pointing on an element of type node. Okay, does this node have an X element? If it does, then I want to modify this next pointer. This is the next pointer I want to set to null if I remove the element right after. But I'm going to remove the element right after only if that element doesn't have an element after it. How do I check this? Well, I'm going to write if. So star list, a row next, okay? And I want to make sure that that element has or does not have an element after it. I do that by accessing its next field. So star list, a row next, a row next. It's a good time right now to pause the video, draw a little diagram to make sure you understand what's going on here, okay? And again, if you have problem, don't hesitate to seek help. We're here to help you, okay? But what I'm doing right now to give you the base explanation is I'm looking at my current node. I'm looking at its next. I realize that there is a next node after that. I'm looking at that next node, and I'm checking if there is a node after that. If there is a node after that, I'm going to do a recursive call. But if there is no node after that, then I can get rid of that node. So if there is a node after that, recursive call. I'm going to come back to that in a minute. Else, I want to get rid of that node, because I know this is the last one, there's nothing after it. So I'm going to call free, and I'm going to call free on star list row next. There we go. And then I'm going to say that the next field of the current node I'm looking at should now be set to null, because I just got rid of the node that was after, right? So I just make sure that I mark the end of the new end of my list. How do I do my recursive call? Well, the beginning is easy, right? It's going to be node del tail, okay? And I'm going to pass the address of a pointer. So what is the pointer I want to pass? Star list, a row next, okay? And I want to pass the address of this little pointer here. There we go. So same logic that we used before for display and stuff like that, okay? And that's my recursive call. What do I have left? Well, I have one possibility left here. After I'm done handling all of this, right, I have the possibility that maybe this first thing that I tested out there was not true. So if star list a row next is not true, that means it contains null. So that means that I'm pointing right now to the first element of a list, and that first element is also the last element. How do I handle this? Well, free this element of the list, okay, and then make sure that the pointer that I have is set to null. So that would be the code that handles the scenario where I have a list. You give me an address of a pointer to a list that has only one element, that's where we're going to handle it. If you give me a list, the address of a pointer to a list that has more than one element, I'm going to be here, and I'm going to look ahead. Is that the last element after this one, or not? If it is, then I can remove it. If it is not, then I'm going to call myself recursively. And that's it for the recursive version. So we're going to save that. We're going to compile and test. So recursive, there we go. Test, I need to actually call it. So I am now using node del tail, and I'm going to say node del front here, and I'm going to call node del tail ampersand my list. And then, of course, as usual, node display ampersand my list, and printf of that /n. Save this. Go back here. Compile. So what do we have? To start off with, we have 42. Then we had 23 at the front. We had 99 at the end. So this is all the add functions. Then we remove the 23 from the front. Then we remove the 99 from the tail. And that's actually what we just implemented in Linky recursive right there. So now we have one variant left to implement. And what I'm going to do is I'm going to take that recursive version, cut and paste it into our iterative version here. Okay. So what I'm going to change now is this is where we do our recursion, right? So what I want to do instead is, instead of saying if the next element exists and the next element after that is also a pointer to more nodes, then I recurse. What I'm going to say is, while this is the case, then I do star list the row next equals star list equals star list a row next. Okay, so this is the way that I advance my pointer star list. So I'm modifying the pointer star list. I'm moving forward in the linked list. I'm going to remove this recursive call here. I don't need it anymore. And I replace my recursion by an iteration with a while loop. Of course, here I don't need an else anymore. What's happening is that once I get out of this loop, then I can do my free. I can set my pointer to null like so. Okay, so I can get rid of, actually no, I cannot get rid of this because I need actually to open a curly brace here. So open a curly brace here, close it here at the beginning of the else. There we go. And this case here is going to stay the same. If I have a list of just one element, then I just get rid of the first element. If I have a list of 0 elements, I don't do anything. So really, it's that case that we had to change to switch from recursion to iteration. Well, let's give it a shot. Okay, let's see how that works. So I'm going to save that. I'm going to go back to compiling the iterative version, run the iterative version, and I obtain the exact same result. So that's it. We've seen a bunch of examples here of different functions that operate on a linked list. As you could tell, all those functions, they can have varying degree of difficulty. Use them as a goal, okay? A goal for your preparation for the final exam. By the time you jump to the final exam, you should be comfortable with this code. If you are comfortable with this code, then there's nothing else I can throw at you that's going to be much more difficult than this, much more involved than that, okay? If you are not comfortable, that means that there are pieces of the lecture that are not making 100% sense. Well, use this module to actually seek help during office hours and get that patched up for you, all right? The last thing that we need to do, there's going to be one more video where we're going to use what we have done here with our linked list library, and we are going to try to implement stack and queues. But I'll see you in the next video for that topic.